All right. Continuing on from where we left off, last time we had looked at how we can figure out acceleration from a graph, and now we're going to continue to finish off this topic 1 of our physics unit. It says calculating displacement during accelerated motion. So it says the displacement of an object during acceleration may be calculated by multiplying the average velocity of an object by the time interval in which it traveled at said velocity. So if you see this formula, this is a formula that we will need to use. I will post today a formula sheet on your Google Classroom so that you can look at that. It'll sort of have all of these on there. So there's an example here that we will try out using this formula. Okay, it says a car merges into a highway with an initial velocity of 65 kilometers an hour east. So again, like I always do, we want to write down all of the things that the question tells us. So our first thing it tells us an initial velocity. So I'm going to write VI is 65 kilometers an hour. What's really important here is that it says east. If we remember, northeast, southwest, east is over here. That's in the positive direction. So I'm going to, instead of putting east on this question, I'm just going to put positive. I like to change it to positives and negatives when we're dealing with calculations just because it makes it easier. It's really like a foolproof way. You can just plug it in the calculator. All right, so continuing on, it says the car reaches a final velocity of 100 kilometers an hour east. So that's our VF. It's east, so it's again positive, and it's 100 kilometers an hour in 4 seconds. So our time is 4 seconds. Calculate the displacement of the car in meters. So we're looking for displacement. Displacement has a little arrow on the top. That's what we're looking for. If we look over at this formula over here, we've got all the pieces we need to solve this. So I'm going to just write this formula up at the top here, and then we can plug our pieces in. So our displacement is equal to our VI plus our VF divided by 2 and multiplied by T. Just going to double check that I did that right. Perfect. So that's our formula. Now we want to plug that into the formula. So I'm going to use a different color here. So our displacement, that's the thing that we are looking for. We don't know, so we're going to put that. Our VI, we do know. It is 65. It's positive as well. Plus our VF, which we know to be 100, which is also positive. I'm going to erase this, put in brackets, so positive 65 plus positive 100 all divided by 2, and then multiplied by our time, and our time is 4 seconds, so we're going to put a 4 outside there. Now we'll go to our calculator. If I do this out, I get 65 plus 100 is 165. And then I'm going to multiply that by 4 and then divide by 2. So our displacement is 330 kilometers. Okay. So that's how you would use that formula. We will try a different one. Sorry, I'm just in the classroom right now and I can hear people walking above me. So someone must be on the roof. Maybe not a good thing. Anyway. Another formula, it says acceleration due to gravity. It says all objects, regardless of their mass, fall to the Earth's surface with an average acceleration of 9.81 meters per second squared. This is a positive number, so they should really put a positive there. This value is referred to as the acceleration due to gravity. So this, if we ever see in a question like gravity, or it's talking about something falling, you're always going to know the acceleration is 9.81. It's something like that is all, regardless of where you are on Earth, that's going to be your acceleration. Note that acceleration due to gravity does not take into account air resistance. So in this class, we don't consider air resistance to be in our formulas or in our calculations, just because that makes it a lot more complicated. So we don't account for air resistance. If applied to the equation for acceleration, this allows us to solve for the final or initial velocity of an object that is falling, as well as the time required to fall. So this is our formula for it, for acceleration, that we just did on the other thing, except for this formula is using acceleration is equal to VF minus VI divided by T. So not this exact same formula, looks somewhat similar, but we've used this, on our other back in this lesson, I believe, but it's just refreshing you on that acceleration formula. But this is this is the main piece that you need, is that 9.81. Something you need to remember. It might be in your data booklet, but it is something that is important to take note of, okay? If they don't give you an acceleration in a formula or in a question, you might realize that, oh, the acceleration is 9.81, okay? Acceleration due to gravity, so let's do an example. This is during a baseball game, a ball leaves a bat and travels straight up into the air. At its highest point, the ball travels at a displacement of 18.5 meters from the bat. Determine the amount of time the ball will take to fall back down to the batter from its highest point if the final velocity before reaching the bat is 11.5 meters per second. Remember, acceleration due to gravity. Okay, so there's lots of information in this question, and one thing that I see right away is they're giving you more information than you need. Some people might get caught up on, oh, it's saying displacement, so we need to use that, but we don't in this question. I'm just going to use, it's telling us we're going to use this formula. I'm going to write down these pieces and see which one we need to solve for. Our acceleration, it says right in the question, remember it's 9.81. This is because we have a baseball falling from the sky. It's once what goes up must come down, and once it gets to its very highest point, it's going to start changing directions and start falling back to the earth. And in doing that, it falls at a 9.81 per meters per second squared acceleration. Okay. It says determine the amount of time the ball will take to fall back down to the batter from its highest point if its final velocity before reaching the batter is 11.5 meters per second. So its final velocity is 11.5 meters per second. And its initial velocity, well, when it's starting from a bat, that its initial velocity should be 0. So it wasn't moving at the first. Or we're basically, and now I need to draw a little picture of this. Think of it like this. This is the, I'm really bad at drawing, but if that was the baseball bat, I'm not even going to draw that terrible picture, but let's say this is the bat and this is the ball. The ball is going to go up and then back down. Okay, so we're actually only looking at from that point at the top to this point. We're not concerned about it going up. We're just concerned about it coming down. So the velocity when it's coming down is 11.5, and its initial velocity is right at this point. So right at the point where it's changing directions, it's actually in that exact second is not moving. So that's why our initial velocity is 0. So when you have these types of questions, your initial velocity is always going to be 0, and your acceleration is 9.81 because it's falling, free fall. Time is what we're dealing with. This is the one we're trying to look for. So that's what we need to calculate. I didn't leave myself much room. Of course, I'm not very good at planning this out. I'm going to just write these pieces of information on the side, and then I'll have enough room to do this question. Okay, so that's all the pieces of information that we need, and then we'll use this space to solve for our missing piece. So in our formula, if we see this formula, this is the piece that we're going to be solving for. So we need to rearrange this formula so that it is set up the way that we want it. You can either rearrange it before you put the numbers in or put the numbers in and rearrange. Personally, I like to put the numbers in, but it's really up to you. I'm just going to put the numbers right into the formula and then rearrange it. So A is equal to, well, we got 9.81 is equal to VF, which is 11.5 minus our VI, which is 0. All divided by, we don't know the t, we don't know the time. All right, so for me, I like to do this. If time is on the bottom, it's divided by t. We need to get it off that bottom, so we need to multiply both sides by t. We do it to both sides because we need to do the opposite, and we need to keep it balanced. So divided by t, the opposite is multiplied. So by doing that, it gets rid of t. And then we're left with 9.81 t is equal to 11.5 minus 0. I'm just going to write, what the heck? I'm just going to write 11.5. All right. So now we're left with this. Now we want to get rid of this t. We don't want to get rid of the t. We want the t by itself, and we want all the numbers to be on this side, okay? So to do that, we need to get rid of the 9.81 in front of the t. 9.81 t is multiplied, so we need to do the opposite, which is divide. So if we divide both sides by 9.81, then we can get rid of that in front of the t, and the t will be left by itself. So 9.81 divided by 9.81 will give you 1. So now you're left with just t by itself. We want that by itself. And then we need to do in our calculator 11.5 divided by 9.81. And I'm just gonna do that out on my calculator. I got 11.7227. So I want it to 2 decimal places. If we write the 3, then we need to check, is this number higher than 5? 5 or higher. If it is, we round this number up. But since it's not higher than 5, we just keep that number the same. So our time is 11.72, and that is in seconds. Okay, so this is our final answer, 11.72 seconds. Another way of calculating displacement during accelerated motion is what is the final velocity of an object. What if the final velocity of an object is not given, but its acceleration is provided? Our original formula no longer allows us to find displacement. Instead, we must use this formula. So this really large formula is something that we're going to have to use, and let's do an example using that. I'm going to just write that formula over here. D is equal to VIT plus 1/2 AT squared. I'm writing it just a little bit more simple. We don't need all those deltas. Probably not, at least. That'll be written on your formula sheet with deltas, but likely not what we need. All right, so as we go through this question, I'm going to write down what's given. I'm just going to write it at the top so that we have enough space to write all this or do this formula. All right, so it says John leaves the surface of a trampoline with an initial velocity of 11.8 meters per second. So this guy, he's on a trampoline and his initial velocity, his VI, is 11.8. So we want to write VI is equal to 11.8 meters per second and travels straight up. So he's going straight up. Determine the displacement of the gymnast after 0.8 seconds. So we've got a time, which is 0.8 seconds. And it's telling us we're looking for the displacement. So displacement, we don't know what that is. If we look at our formula, if I can get on the right thing, we've got VI, which we've got in our thing right here. We got T, which we've got T here. We've got A, which we don't have right here. And we have T again. So we're still missing A in order to figure out our displacement. So to figure out our A, remember, this says we have acceleration, or we normally do have their acceleration, and our acceleration, because this is going straight up, we know that acceleration is going to be due to gravity, and it's going to be 9.81 meters per second squared. Okay? So now we can use that pieces of information to solve for the missing link here. So let's plug in all the pieces to our formula and see what we can solve. So our displacement is what we're trying to figure out. Our VI we know is 11.8 multiplied by our time, which is 0.8, plus 1/2 times acceleration, which is 9.81, times our time, which is 0.8. And that's all squared. Oops. So if we grab our calculator, I'm just using my iPhone. So you can do this on your iPhone if you just turn it sideways, because you can't do squared on the original calculator. But if you do sideways, I just have to turn my lock off. Doesn't seem to be working. Okay, perfect. So now if I have it sideways, I can do 11.8 multiplied by 0.8. I'm just going to do this in steps, just so that it goes okay, because I don't have a calculator that I have brackets. Plus 1/2 times 9.81 times 0.8 squared. I'm going to do the 0.8 squared first, because we're doing our bed mass. We do brackets, exponents. So we've got exponents, so I'm going to do 0.8 squared, which gives us 0.64. Times 9.81, and then 1/2 of that. Moving down, I will calculate all that, so 0.64 times 9.81. Sorry, I'm not getting the decimals in there. Divided by 2, or times 1/2. Gives me 3.1392 plus 944 from the top there. So now if I take those two numbers and add them together, I should be able to solve for my displacement. Remember, this is displacement. I should have an arrow there. And the answer I get is 12.5792. We want to have 2 decimal places, always. So we would get rid of that one. We got to look at this 9. Is it higher than 5? It is, which means this number is going to go up. So our final answer should be 12.58. Okay? And this is a displacement, and it's in meters. Why is it in meters and not kilometers? Well, I look back at the question. It's got meters per second, so we know it's in meters, our answer. Okay? So that's how we calculate that, using that formula. And then the last thing that we need to go over in this little section is on stopping distance. So it says the principles of acceleration can also be used to determine the distance a vehicle requires to stop when traveling at a certain speed. Before the vehicle begins to brake, it's traveling with a uniform motion. Once a vehicle begins to brake or decelerate, it is traveling with a non-uniform motion. So when we're going in our car, let's say we're in cruise control, we're going at a uniform motion, then a red light is up ahead. So we see the red light. There's a time between the time we see the red light and we put our foot on the brake, and then once we put our foot on the brake to when we actually stop. So they've split that into these 2 separate pieces. This is our reaction time, and then this is our braking distance, okay? So there's 2 separate times, and all of those together they add up to our stopping distance. So our reaction time and our braking distance. Okay, those are all connected into our stopping time. It says we have some steps here on how we can calculate this. It says calculate the distance traveled while the driver reacts. So the distance traveled while moving with uniform motion. So that's just how we've done before. Our reaction time is going to be connected into our velocity is distance over time, because we should still be moving at a uniform motion. Okay, so that's our time of reacting. Number 2, we calculate the distance traveled once the driver starts braking and the distance traveled while moving with non-uniform motion. To do that, first we use the rate of deceleration given to calculate the time required to stop. So we use this formula here. It's already rearranged for you. Okay, so that's the formula that we use. Wow, everything is in the way. That is how we figure out the distance traveled while moving with non-uniform motion, while you start to brake. Then we use the time required to stop, initial and final velocity of the vehicle provided to determine its displacement. So using this formula here, add your answers from step 1 and 2 together to get your total stopping distance. So this is like a 2-step process, well, 3-step, I guess. So you calculate, this is what you use for reaction time, because you're still in uniform motion. Then you use this formula to calculate the distance that it took you to stop. And to do that, you need to figure out the time, so you use this formula. So it's I guess like a 4-step process: reaction time, and then this is for stopping. And then once you've got all of those numbers, you can add them all together at the end, and that should give you your stopping distance. We're going to do an example of that. I might not have enough room here because these questions tend to be quite extensive. I'm just going to copy this into a note. Oh, I'm already in a note. Copy it into a new note. Which is still inside of here. And then we can use this, I think. Maybe not. Let's just go into a new note. Just getting it's working. All right. So it says the typical reaction time for most drivers is about 1.5 seconds. A vehicle traveling under typical conditions is able to decelerate at, this 2 is supposed to go here. You know what? I'm going